everybody else. There's various bits of noise coming through, which I'm going to mute everybody. And Laura, when the time comes, you may unmute yourself. There we go. Right, let's stop that. Here we go. Right. So Laura Hayes is our guest this evening. Now I've got to unmute me. No, I'm unmuted. I'm all right. And Laura is a solar physicist who currently works as a research fellow at the European Space Agency at ESTEC in the Netherlands. She received an undergraduate degree in theoretical physics from Trinity College, Dublin, Ireland, and soon after joined the astrophysics research group at Trinity to complete her PhD in solar flare physics. Following her PhD, she joined NASA Goddard Space Flight Center as a postdoctoral fellow for 2 years, where she continued to work on solar flares with a focus on X-ray observations. Research makes use of both space and ground-based observations of the sun in multiple wavelengths to help build a better understanding of the physical processes that underpin solar flare energy release. In particular, she's involved with ESA's Solar Orbiter mission, which launched in 2020, and which is now providing new and unique observations of the sun. Of course, with solar cycle 25 beginning to look really quite interesting, there's no better time to be involved in the sun. So tonight's talk, The Active Sun, Observations of Earth's Closest Star. I will hand the floor over to Dr. Laura Hayes.
Great, thank you so much, Paul. Let's see if I can share the screen. Hopefully this all works. Is this looking okay?
Yes.
And you can hear me okay?
Yes, I can indeed.
Fantastic. Okay, great. Well, thank you, Paul, for that introduction, and thank you for having me here today to talk to give this lecture of the IAA. So I am a solar physicist, as Paul mentioned. So I really, look at the sun all day, every day. And I particularly look at it in lots of different types of observations. So I hope in this talk, what I'm going to give to you is more of kind of an overview talk of our active sun, why we care about it, why we're interested in these solar flares and solar eruptive events, what that means for us here on Earth, and where we are kind of right now and looking into the future, as Paul said, for solar cycle 25, which is really exciting. So what are the kind of unanswered questions, and what do we hope to solve with new observations, particularly with ESA's Solar Orbiter, which I'll talk a little bit about in the end. So some of this may be familiar to you. You may have heard about other talks about the sun, but hopefully you'll gain some new insights into kind of the interesting topic that I find of solar flares. So this is a nice kind of movie in the background. Hopefully you're seeing it, really to highlight, I guess, that the sun is super active, right? I mean, it's not just a yellow ball in the sky. The atmosphere of the sun is really, really complicated and diverse. And just to kind of take a step back, when we maybe think about the sun, if we took a ground-based telescope, you take one of your telescopes that you have maybe at home and you put a solar filter on it, and you looked at the sun in white light, it might look something like this. So this is a white light observation of the sun taken with the Solar Dynamics Observatory. You can see, it doesn't look super exciting, a yellow ball in the sky. This is the Earth for scale, so to really show the magnitude of how large the sun actually is. And this is what we call the photosphere of the sun, or the surface of the sun, the lowest lying atmosphere of our closest star. The temperature of the surface of the sun is around 5,000 degrees Celsius. So by no means cool, it's quite hot, but we'll see in a minute it's not actually as hot as when we go out further regions of our solar atmosphere. Other things to maybe note in the photosphere are these dark regions, which many of you may have seen before in observations with your own telescope or pictures in the past. And these are sunspots. So these are intense regions of magnetic field that are so intense that they actually inhibit convection, so they appear cooler on the surface of the sun. Now again, looking at this yellow ball, if there was no sunspots, it looks fairly boring, not much is going on. But it's really when you go out into the atmosphere of the sun, further out into the chromosphere, this is moving away from the surface of the sun, you really start to see how diverse and dynamic the atmosphere of the sun actually is. So this is an observation taken again with the Solar Dynamics Observatory, NASA's Solar Dynamics Observatory, and it's looking at extreme ultraviolet wavelengths. So it has a filter to pick up just those wavelengths. And this is in particular looking at the 304 angstrom channel. And again, two things to note here. First of all, when we go further away from the sun, it starts to get hotter, and really hotter, right? So we're going from the surface, and you go out a few thousand kilometers, and you go up to 50,000 degrees Celsius. So again, it's getting hotter, and we can see there's a lot more structure going on. So these two images are taken at the same time, and we can see over these, sunspots, which I talked about being strong magnetic field, we see these bright hot regions in extreme ultraviolet. So that's showing us that there's even really, really hotter plasma than 50,000 degrees Kelvin or Celsius in this region here. And it's harder to see the other dots here, but you can see there's a sunspot here, there's a sunspot here, there's a sunspot here. And then when we look in the EUV, or this extreme ultraviolet wavelengths, we can see that there's hotter regions of the sun over those intense magnetic fields. We can also see structures like this. This is called a filament, or a prominence if it's off disk. And this is cooler. So this is why we see it in dark in EUV channels. And this is kind of hot plasma or cooler plasma that is suspended slightly higher up, held by the magnetic field of the sun. And then again, this is an active region, as I mentioned, if we go out even further and we look at a different extreme ultraviolet channel, so this is looking at 131 angstrom, so it's similar to kind of close to X-rays that we're seeing from the sun. We can see again that, we see this structure even further. We see these active regions. And something to note is we see that the temperature of the sun or the atmosphere is getting even hotter. We go to 5 million degrees Kelvin or Celsius. So again, just one takeaway is, the atmosphere of the sun gets hotter and hotter the further away you move away from it, from the surface, which is something we still don't understand. And this is known as the coronal heating problem. It's like if you walk away from a fire, it should get cooler. However, we find that it actually gets hotter in the case of the sun. And there are several theories to kind of understand how the energy is transferred to heat up the atmosphere of the sun, but it's something we still don't know. And again, just focusing in on how dynamic these active regions or even the whole sun is, we can again look at, say, this one active region in 3 different extreme ultraviolet wavelengths. So we're looking at 3 different filters on Solar Dynamics Observatory, and we can also look at the magnetic field map. And hopefully these movies are playing. This is actually showing an active flare. So this is this bright, intense occurring thing that occurs in these active regions. And the energy is absolutely enormous. And that's what I'm going to talk a bit more in this talk. And something to note, this is, again, as I said, a magnetic field map. So these active regions are strong magnetic field regions over sunspots. And they also are quite dipolar. So this is showing the positive and negative aspects of the magnetic field. So there would be a loop occurring between these two, which you can kind of see in the EUV image. And typically when you have regions that the magnetic field is getting twisted between the positive and negative polarities is when you get this complex magnetic field and you're more likely to have a solar eruption. But again, to kind of further highlight the dramaticness of the sun and the atmosphere of the sun, this is going to show a movie over a period of time where there's a large eruption that's going to occur on this region of the sun here. So if I play this movie, we can see this huge eruption go out, but all other portions of the sun you can see is continuous in motion. It's a hot ball of plasma that is continuously moving and erupting and emitting things into interplanetary space. Now we saw that eruption, but if we zoom out and look at a coronagraph, so this is looking at ESA's SOHO mission, we block out the main light from the sun and see how this ejection actually expands into interplanetary space. It really just shows how dramatic these eruptions are away from the surface of the sun. So again, if you go back and think about that, the first image I showed were how tiny the sun actually, or the Earth is in comparison to the sun. And then we're seeing how massive these eruptions are compared to the sun. If we are in the path of one of these eruptions, this is something we need to consider, and it can be something that can have a direct impact on the near Earth environment. This is something we would term in terms of space weather. So how these eruptions and solar wind and the things emitting from the sun has impact in the near Earth environment. And similarly has impact on other planets. So it can have impact on Mercury and Venus and Mars and on the further out planets, and also things in its way. So any type of satellites, we think about, astronauts that are in space, and something we really want to consider just to show you how dramatic these eruptions are. So just some terminology, the term solar flare I've talked about just a moment ago. We also hear things like coronal mass ejection or CME. And these two are different things. The radiation is the portion, so just the light being emitted by this energy release is the solar flare. And then that eruption of material, that eruption of hot plasma magnetic field away from the sun is called the coronal mass ejection. And these two things often occur in tandem, and this is what we would call a solar eruptive event. So here I'm going to show another movie from one of the largest flares of the past solar cycle. This was an X8, which will make a bit more sense in a moment when I talk about the magnitudes of these flares. So on the left-hand panel here, you can see this brightening in these bright loops. That's the flare portion, the bright emission across the entire electromagnetic spectrum. This is only showing extreme ultraviolet light, but if you looked at radio waves through like infrared, through even sometimes invisible light, all the way to X-rays and even sometimes gamma rays, you see emission increase from the sun during a solar flare or the solar eruptive event. And then usually accompanying this solar flare, which happens lower down in the solar atmosphere, is again this ejection of material, which is called the CME, or the coronal mass ejection. This one was so dramatic actually that we can even see all these kind of speckles in the CCD of the imager, the coronagraph imager here. And what this is actually energetic particles that are accelerated during this solar eruptive event that are actually interacting with the CCD on board. So it really just shows you how grand and how large these eruptions can actually be. And I guess a reason to why we care, and something I've alluded to, is, you know, we live in the presence of this active star. So not only do we have solar eruptions, we have solar wind, which is this continuous streaming of particles away from the sun. You can have a fast solar wind and a slow solar wind. You can have these highly energetic particles, so like ions and protons are accelerated extremely fast away from the sun. And then of course you can have these coronal mass ejections, which is material away. And then of course you have the radiation portion. So, you know, you have the radiation which creates our ionosphere. But kind of when you have a flare, this ionization increases dramatically, which can have a significant effect. But luckily for us, as kind of shown in this cartoon drawing here, the Earth has quite a strong magnetic field, which protects us as humans, I guess, on Earth from these energetic solar eruptive events, which is great. And one of the nice things I guess we do see is the Aurora, and I'm sure many of you have seen them in the past. I know particularly from portions of Northern Ireland, you can get really nice images of these aurora if you have a clear night and a large solar storm passing. But they can also have adverse effects. Now, you know, we've known the sun has been, you know, erupting and quite active for a very long time. And one of maybe the first cases of most famous solar eruptive event is from observations from Richard Carrington in 1859. This is known as the Carrington event, and it's the first kind of well-observed, or maybe one of the first observed solar flare ever that was recorded by a person or by an observer. So Richard Carrington at the time was drawing daily sunspots. So you would look through your telescope and you would record daily sunspots with these really immaculate drawings on the surface of the sun with really good accuracy of the positions of these active regions. And just by sheer luck that he was looking through the telescope at the time of the solar flare, he actually managed to identify these intense brightenings within the sunspot region. And he actually drew them here. And what we see today, these are known as ribbons, white light ribbons, which is crazy that, you know, these things only occur for such a short period of time when you can observe them in white light, that he actually was able to see these. I guess the interesting thing about this observation was that it was the first time that it was noted that, you know, you have this large solar flare that Carrington observed in white light, but 17 hours later, there was a huge geomagnetic storm recorded in ground-based self-recording magnetometers at the time. And Aurora was observed, you know, at very kind of much lower latitudes than would usually have been observed. And here is a clipping actually from the newspaper on September 2nd, which talks about the auroral display. So if you read this here, it says the auroral display of last night was so brilliant after midnight that ordinary print could be read by its light. So this is something that in recent years, since this event, we have never seen the likes of. We've never seen a solar eruptive event so large. And, you know, this is what we talk about as solar physicists. Will a Carrington event ever occur again? And why it's important, why we're kind of talking more and more about Carrington events, is that at the time in 1859, the only real, you know, significant telecommunications or technological infrastructure that society was depending on that was susceptible to such solar event were telegraph wires. And there was, even in this newspaper clipping, you can see there was an extraordinary effect was apparent on the national telegraph wires. And what actually happened was that the telegraph wires, there was induced currents in the wires, that they found that even when they turned them off, there was a few sparks occurring. When they turned them off, they were still able to talk to each other because there was currents flowing through caused by this solar storm and its interaction with the near Earth environment and our magnetosphere. But, you know, we've come a long way from 1859. We are now a society dependent on a huge amount of technological infrastructure from all our parts of life, you know, especially during this pandemic, if you think about it. And here is a nice infographic, I think, to really just highlight some of the portions of modern society that are super susceptible to these solar eruptive events that I talked about. So one of the things that's really talked about at the moment, I guess, is when you think about astronauts in space, or even people, the astronauts in the ISS, or if we need to go back to the moon, we do not have a strong protection of the Earth's magnetic field. So as we're talking about going back to the moon, you know, 2024 and onwards, and particularly when we're talking about going to Mars, you have to send astronauts to space unprotected for a very long time. So we need to be able to have really good forecasts to be able to predict when they can go for spacewalks, when they should be protected. And this could be, you know, it could have a serious damaging effect, which could be lethal in some cases, particularly with highly energetic particles to astronauts in space. But something more everyday life, I guess, we need to think about is that when you have a solar flare, it can impact the ionosphere to significant amounts to disrupt high frequency radio communications for several hours. So if anybody works with ham radios, you might be familiar with when you have a flare, your ham radio goes out. But this is particularly important with emergency responders that particularly use high frequency radio communications to communicate. So we don't want to have a radio blackout for extended periods of time. Of course, all our satellites in space, even I showed you that example with the detectors on board, these are susceptible to energetic particles that come from the sun. And also you can have increased atmospheric drag caused by a solar flare. So the ionosphere essentially swells and then you get further drag on your satellite. So it can reduce lifetimes of satellites. And then other things like, you know, if you're going in any way of a polar flight during an event, you can have as much radiation as 2 chest x-rays. And then in the case of you have an extreme solar event, you can have things like you can have power grid blackouts where your transformers burn, or you can have disruptions in your oil pipelines. So really, you know, we want to think of space weather and understanding the sun in 2 ways. We want to be, you know, preventative on short scale things that might kind of slowly damage our technological infrastructure, but then also catastrophic events like this Carrington event that may only be 1 in 100 years. If that happened, what would the impacts be on daily life, and how can we mitigate those effects? How can we prepare, you know, our infrastructure for an event, and how do we get better forecasts to be able to, you know, turn down power grids or open transformers, et cetera, et cetera. So this is kind of a motivation, I guess, about why we want to study the sun, particularly from a space weather aspect. And much has changed from Richard Carrington's days where you were drawing daily sunspots with your telescope, your home telescope. We now know that the sun emits light across the entire electromagnetic spectrum, as I mentioned, from gamma rays all the way up to low frequency radio waves. And we want to be able to essentially observe the sun in all of these wavelengths, mainly because each of the wavelengths that it emits in tells us something different about the sun. It can tell us a little bit about the different physical processes that occur. So I guess we have to think then again about the solar atmosphere. The solar atmosphere blocks out lots of different light. It blocks out X-rays, which is a good thing. We don't want to have X-rays coming down and interacting with us on the ground. It also blocks out a lot of ultraviolet light, such as the light we see these beautiful images in, and infrared. So this is why we need to have both space and ground-based observations. So this is a nice plot showing kind of the opacity of kind of what wavelengths can get through as a function of wavelengths. So we can see obviously visible light can get through and radio waves can get through. And then basically for all other wavelengths, we need to go to space. But we're in a kind of a good position that the sun is so close that we can have absolutely gorgeous observations. And, you know, we are hugely data rich in the field of solar physics. And just to kind of give you some examples, going back to kind of ground-based instruments, particularly European-based instruments, in the Canary Islands, we have the Swedish Solar Telescope, which is optical. It takes absolutely gorgeous images of the sun. So this is an image of a sunspot in immaculate detail. So some of the best images we've ever been able to see in optical astronomy looking at the sun. And this is the proposed European Solar Telescope, which is very exciting. It's going to really tell us lots more information about the really high resolution information of white light observations of the sun. But of course, being in Ireland, we can't have an optical telescope to look at the sun. It'd be quite pointless. But luckily, radio waves can get through. And I'm sure many of you have heard of ILOFAR, or have been, of course, to Birr Castle to see ILOFAR. But ILOFAR is a large radio telescope which looks at 10 to 240 megahertz. So kind of the cutoff limit, the lower end of the frequencies up to 240 megahertz. And it's part of a larger network of radio telescopes all around Europe. And this is really nice that we can look at the sun in these low frequency radio waves, which tell us an awful lot about particle acceleration and shock acceleration of these energetic particles. And one of the nice things about the ILOFAR station is we're given some time to do our own type of observations. So we've been doing really high resolution timing observations of solar eruptions. Now, when we go to space, it's a different story. We can see all the light. We don't need to worry about our atmosphere. And here's just a snapshot of what we would call maybe the NASA Heliophysics System Observatory. So this is the suite of instruments that are really only looking at the sun and are near heliosphere. And really just to show you the magnitude of why we are becoming so much more data rich as solar physicists. So we have SDO, so this is the Solar Dynamics Observatory that take these beautiful images in extreme ultraviolet waves. We also have SOHO, which takes these coronagraph images, RESI, which is an X-ray imaging spectrometer, which is recently turned off, but it takes X-ray images of the sun. And really just to kind of highlight, I guess, how much we as a society care about understanding the solar terrestrial relationship and how important it is, both from a physical point of view of understanding the sun as a star, but also from a space weather perspective to see how the sun impacts, our nearest environment. One of the most exciting things, I think, is ESA's Solar Orbiter, which was launched in February of last year, so just before the pandemic. And as of this month, we are now in our nominal science phase, as in 2 days' time. So we're now, in our prime science phase to really get some new and exciting observations. And we have lots of observations from last February when it was in its cruise phase, when we were doing a lot of calibrations. So it's a really exciting time in solar physics. And if you take a step back and talk a bit more about, solar activity, why do we have a sun that has a really complex magnetic or really complex atmosphere, and why does it have these solar eruptive events? We need to go back and think about the sun's magnetic field, because that's really the underlying element here. And we need to think about the sun not as a solid surface like the Earth, but it's a plasma. So it's a highly ionized gas, so it doesn't have a solid surface. And what this means is that it doesn't rotate like a solid, it rotates differentially, meaning that the middle of the sun is going to rotate faster than the top of the sun. So if we think of magnetic fields that is embedded in the plasma, when the sun starts to rotate, it's going to rotate at different angles and different speeds. And essentially what we have is a magnetic field that gets intensely complicated and twisted, and you have a lot of potential energy then stored within the magnetic field. And this is essentially why we have these solar eruptions and why we have this kind of active solar atmosphere. And it follows a pattern of going from really, really complicated, as we see in a moment here, when it's really in a big hairy ball mess, and when it goes to straight, and that's what we know as the solar cycle. So it gets super, super twisted, it gets super, super twisted, it starts to unwind again, goes back to normal, and then gets super, super twisted again. And this is what we know as the solar cycle in very simplistic terms. So the sun goes through the solar cycle every 11 years, where it goes through a period of minimum activity, where not much is really going on in the sun, to maximum activity, where the sun is really active in terms of solar flares, lots of sunspots, lots of solar eruptive events. And we can track this based on sunspot numbers. So this is even just showing the last 3 solar cycles from 1984, looking at sunspot numbers. So we can see, maximum and minimum. The last maximum was around 2014, went down. We've been in a period of very low minimum for the past few years, but now it's starting to ramp back up again. As Paul mentioned, so we're now into solar cycle 25, so it's exciting. The sun is becoming more active, particularly as a solar flare physicist. This is particularly exciting. Now, I've been talking about solar flares, but how do we kind of classify solar flares and what do they look like? Now, we classify solar flares based on the X-ray emission that is emitted from the sun. And the reason we do this is because when you have a solar flare, it's the X-ray flux from the sun that increases by orders of magnitude compared to the other wavelengths. So for example, in optical light, it's very difficult to see a solar flare because the sun is so bright in optical, it doesn't it doesn't increase that much. But in X-rays, as we can see here, it can increase by several orders of magnitude. So this is a time series plot looking at the X-rays integrated over the whole sun over an active day in 2013. And each one of these peaks is essentially a solar flare. And we classify solar flares based on their peak intensity that we see in these observations. So if it peaks here, we can say it's an M-class flare, but if it peaks above this line here, we say it's an X-class flare. So in terms of magnitude, A, B, and C-class flares are pretty small, not that exciting. But when you go to M and X-class flares, this is when we have usually large solar eruptive events, and these are the kind of flares that would have an impact from a space weather perspective. And just to highlight, I guess, if we look at we plot each of these peaks, each of these solar flares as a function of time, we can see that it really does follow this solar cycle. So each of these points is a solar flare, and this is the peak flux. So, this is one of the largest flares of the solar cycle. And when we overplot the sunspot number, of course, then you see that it nicely follows this solar cycle. And again, if we just kind of highlight the last solar cycle, and to kind of give you an idea of how often these large events occur, over an 11-year period, there was only 49 X-class flares. Now, the last solar cycle was particularly small, but when we're talking about over an 11-year period, there were only really 50 large flares that are going to have a significant impact. And again, if we look at the distribution of these flares, we can see the number of flares as a function of peak flux. So the takeaway, I guess, here is that there are lots and lots of small flares, and there are very, very few large flares. And we're kind of interested, I guess, in how this line or this slope of this line is in case of solar flares. And this is important to go back to this idea of the coronal heating problem. As I said, the atmosphere of the sun is hotter than we physically understand. It's hotter than the surface of the sun, and we don't know how the energy is transferred. And maybe it is just a fact that this power law extends down. So there are smaller and smaller flares that we can't even see with our current instrumentation that are actually heating up the atmosphere. So this is why people are interested in looking at solar flare distributions and how these change across wavelengths, and maybe looking to see how the slope is, because if it is around 2, then we can say that yes, it is tiny, tiny flares that are causing this coronal heating. What I also think is interesting when we think of our star, this is there's a lot going on in this plot, but our star is a very average star, it's a G-type star. But we know of other stars similar to our own sun that have even larger flares than we've ever seen, larger than the Carrington event. And the question is, this is super flares that are observed that extend down. So these are the tiny flares, these are very large flares. This is the largest flare we've ever observed on this energy scale. And the question is, will our sun ever produce a flare larger than that? And by looking at statistics of other stars, the question is potentially yes. Maybe it's just a 1 in a 1,000-year event that we just haven't been observing for that long yet. So I think this is just an interesting concept to think of the sun as a star and where it fits into other stars in our galaxy and beyond. Now, just to kind of give you some characteristics, some takeaways, I guess, how long do solar flares last? So they can occur from minutes to hours. So here's an example showing 3 different observations looking at X-rays. So this is soft X-rays, so close to extreme ultraviolet wavelengths, hard X-rays and radio, and this event occurred for around 20 minutes. Where do they occur when we're looking at the sun? I mean, they occur in these active regions, as I mentioned, in regions of complex magnetic field that are overlying sunspots. And you usually see this nice loop type structure in these active regions. And this is where most all of large flares particularly occur. And I guess going back to a solar flare, so this is the radiation portion of a solar eruptive event, is there also always an ejection of material? And the answer is no, but in the cases that we really care about, it is quite more like yes. So it's almost 100% of X-class flares have a solar eruptive event. So I guess the question is, why do only larger flares all have an eruptive event? This ejection of material, and are smaller flares similar in characteristics to these larger flares? And what is our current understanding of how these occur, and what is really driving these events to happen? So I'm going to just walk through a standardized model of our interpretation of how these events occur. So first we have this cartoon where we can see this we see this magnetic field lines start to rise and then they reconnect. So this is the magnetic field lines reconnect together to release the magnetic energy that is stored within those twisted magnetic fields. And if we observe, this is an actual observation, and it really does show that cartoon structure where you have this rising filament that then ejects away, and then you have energy release that goes back towards the sun and then away from the sun. So it's the magnetic reconnection that's really the driving force behind these eruptions. And the energy is nothing that we could ever compare to really on Earth. And if we think of this cartoon model where we have energy release, this magnetic reconnection that occurs a little bit higher up in the solar atmosphere, then we have the magnetic loop underneath, and we have the CME ejection, this coronal mass ejection away from the sun. And if we step through these different portions, we have this energy release. What this energy release does, it accelerates the charged particles in the solar atmosphere. So these are charged electrons and of course, ions. It accelerates these particles to really, really high energies and efficiently accelerates them. It accelerates them to energies and efficiently accelerates them to points that we don't really still understand. These accelerated particles are then going to start emitting in different wavelengths. Those that emit away from the sun are going to emit radio bursts, low frequency radio bursts that we observe with, for example, LOFAR. Those that penetrate down closer to the sun are going to spiral along magnetic field lines to emit microwave radio observations. And then those accelerated electrons are going to then interact with the denser regions of the atmosphere, and then they're going to emit in hard X-rays. So really high energy X-ray are going to be emitted from these, what we call foot points. And then again, if you think of this as 3 dimensions, these extend out into ribbons. And this goes back to this Carrington drawing, what he drew these ribbons. What he was drawing was actually these foot points of this flaring loop, which is super interesting. And then you have this heating of the plasma caused by this energetic particles, then fill the loops with really hot plasma. And you have this emission then in soft X-ray in extreme ultraviolet wavelengths. And the reason I guess I want to highlight this is that it really is a multi-wavelength process. We have radio waves, we have microwaves, we have EUV, we have X-rays, we sometimes even have gamma rays. So to really understand this whole process, we need to be able to observe the sun at all these different wavelengths and from both space and ground-based observations. So it really is across the entire electromagnetic spectrum we're seeing emission. And why this is interesting, I guess, as well, is that we have increased solar output. So I showed you a plot of X-ray emission increasing by orders of magnitude. But you can also have extreme ultraviolet wavelengths that increase by orders of magnitude. And all of these things have an impact on the ionized portion of the Earth's atmosphere, another element of space weather that we're really kind of need to think about, particularly as I go back to mention high frequency radio communications, because this is what actually blocks them out. Now we have a nice model to describe how these solar eruptive events occur, and they piece together and they describe a lot of our observations. However, we still don't know lots of things, and I just want to highlight some of the many open questions that we're currently trying to solve with our current observations and future observations that really help us to understand, the physical processes occurring in these solar eruptive events in an aim to then build better predictive models of when they're going to occur, how large they're going to be, how long are they going to last for. So some of the open questions are the triggering mechanisms. So I just said you have this energy release, but what actually triggers that? What is the key point then, critical point for the energy to build up, and then release? We still don't know. In terms of accelerating these particles, these charged particles after the energy release, we don't know what the acceleration mechanism is. We don't physically understand how the charged particles go from 0 to non-thermal in such a short period of time. In terms of the transport mechanism, we don't really understand how the energy gets from this reconnection region, so this region where the magnetic fields break, down to the regions of the chromosphere, and how does the energy change as it's transported down, and how does that impact then our observations and our interpretations of our observations. And for a lot of cases, after say the most energetic energy release that we observe in X-rays, for example, we sometimes see continued levels of emission for several hours, and we would call this the decay phase of the flare. But we don't understand what the energy input is into this, and something we really need to kind of think about if we're trying to build a better flare model. And I guess, we want to answer these questions to be able to build towards a better understanding of why, how, and when these things are going to occur. And this kind of leads on nicely to the exciting new prospects that ESA's Solar Orbiter brings. So I mentioned, yeah, it was launched last year in February. It was launched from Cape Canaveral in Florida, and it went on its mission to the sun. So on board ESA's Solar Orbiter, there are 6 remote sensing instruments. So these are instruments that are taking, they're taking an image of the sun, or they're remotely sensing something. They're not actually probing anything. And then the in situ instruments are things that actually are probing, the magnetic field or the temperature, or things like that. So we have 6 remote sensing and 4 in situ instruments. And I think what's interesting is that all of these things are on the same platform. So we can use images of the sun together with a probe to really get a better understanding. And just to kind of show you the uniqueness of Solar Orbiter and why it's exciting compared to previous missions, is here is a movie to play of the orbit of Solar Orbiter over several years in 30 seconds. So we can see it was launched, and as you can see, the Solar Orbiter is here. We can see Mercury, Venus, and Earth, and it has a very different trajectory to what we're used to looking at the sun. We usually observe the sun from all the instruments that I showed previously, in geosynchronous orbit, or we're at Earth, so we're getting the same perspective. But what's exciting about Solar Orbiter is that it's going to go really close to the sun. First of all, it's going to go inside the orbit of Mercury, but it's also going to go out of the ecliptic plane. So it's going to see kind of closer to the poles of the sun, observations we've never been able to see before. So this is what we really find exciting. So again, the 2 things are, it's going to get a different perspective from Earth, so we'll be able to do stereoscopic measurements, and the fact that it's going to go out of the plane. So we're going to see poles, the poles of the sun, and we're going to get really close to the poles of the sun. So we're going to be able to take images of things we've never been able to image before. So we don't, it's almost exciting to know what we'll expect. And something to note, actually in 2 days' time, the Solar Orbiter is actually doing an Earth flyby. So it's going to come the closest it's ever been to Earth, and it will ever be again since launch on the 27th of November, which is also cool. So some of the kind of just the key points of what Solar Orbiter can really do. Here is a cartoon image of what it looks like and all the different instruments on board. So I won't go into all of the details of the different instruments, but here are some of the science highlights that have already been observed with Solar Orbiter during its cruise phase. So this is an image it's taken, and it can also take these really detailed close-up images, and it's seen these campfires. So they've seen these tiny little brightenings in the extreme ultraviolet observations of the sun, which we think potentially could be these tiny flares that I mentioned. So maybe that distribution does continue, and there are lots and lots of tiny flares that are heating the solar atmosphere. And it's also taking lots of different spectra. It's taking magnetic field measurements. We're taking radio observations. So it really is super exciting. And from a solar flare perspective, what I think is super cool and what I'll be working on is that before we took images of the sun, and maybe we had a different instrument that was maybe probing the energetic electrons, and then we had a ground-based instrument that was looking at the radio wave observations. But now we have all of these instruments on the exact same, on the same spacecraft. So as it's flying, it's going to be able to image the sun. So this is the image here. So it's going to image this, say, for example, a solar flare in eruption. It's going to be able to image it in extreme ultraviolet wavelengths. It's then going to be able to image it in X-ray. So that's what these contours are here. We can then take the energy spectra of those X-rays, and we can kind of make some nice plots here to understand, the accelerated electron distribution. And then for the in situ measurements, so this is looking at the energetic particles, so we can actually measure the electrons that are emitting away from the sun, as well as those that precipitate down to the sun, and then compare the two. And then we can also take these radio observations to understand, these energetic particles that pass by. So it really is going to change the game from really understanding solar flares and solar energetic eruptions, and kind of hopefully answer some of those questions that I mentioned when I was talking about the things we still don't know about solar flares. And then one final thing I wanted to mention is, because Solar Orbiter, it has a different perspective to Earth, it allows us to do stereoscopic observations. So it's going to be able to allow us to look from 2 different points of view at the same solar flare. And this is something we've never been able to do with X-rays before. So Padre is a CubeSat instrument that was recently selected by NASA, which is going to fly the X-ray imaging detectors on board, which will then allow us to look with the same detectors at a solar flare and be able to understand some of the energetic acceleration processes that I mentioned before. And now I'm aware of time, so I'm going to be finishing up soon. It's an exciting time ahead. So this is a plot from 28th, so late last month. We had our first X-class flare of the past solar cycle. And this is an image taken, and we can see that the sun is starting to be active again. We see lots of active regions going on. And it really is an exciting time. We have new observations with Solar Orbiter, and we have new observations with LOFAR. We have all the different instruments that were around through the last solar cycle, and some that are proposed and will be launched very soon, and new data coming down soon. So it's really exciting time to be a solar physicist for sure. So just to conclude, I guess, when we're talking about solar eruption events, they consist of both the solar flare, which is the radiation portion, so the X-rays and the EUV and all the different electromagnetic emission we see, and then the coronal mass ejection, which is ejection into interplanetary space. And these can both have adverse space weather effects. And I tried to kind of list a few. And really, solar flares are a truly multi-wavelength phenomenon. So we really need to be able to observe them with lots of different instruments from both the ground and from space. And I think we're really getting this every day. We're getting a better view and understanding of the sun in this way. There's so many unknowns, which I tried to highlight, but I think these will be really, if not solved, but highly constrained with the new data from Solar Orbiter. And I guess a note I'm sure you already know, but over the next while, the Aurora will hopefully be more and more common. So I hope that we'll be able to see it over the next solar cycle. So that's all I kind of wanted to say. I have a last little movie about the flyby that's going to happen in a few days, but I'm happy to take any questions, and I hope that was okay for time.
Right. Thank you very much, Laura. That was superb. You've got the movie there, is it?
Oh yeah, sorry, I can play it here. Yeah.
Go on.
This is So hopefully this is playing now.
Yep.
So oops. Let's see. So this is on the 27th. Unfortunately, we won't be able to really see it from Ireland. So this plot is going to show you what it will look like flying over Earth. This one here shows, this is the Earth here is a polar plot to show how fast it will come in. This is looking at the angular diameter, how big it will be in the sky, and this will be the distance to Earth. So when I play this movie, we can see it's going to do a swing by. If you are maybe in Tenerife or in Morocco, you might get a glimpse of it before it goes into the Earth's shadow. But it's going to come as close as 470 kilometers in altitude, as close to the Earth. It's also going to move very fast. It's going to be around 0.13 degrees a second. So I don't even know if you'd observe it with a telescope. You might even need a pair of binoculars. But I think it'd be exciting. I wonder if some astronomers will be able to actually observe it. But it'll go on its way against Solar Orbiter, and it will never come as close as it's been before. So yeah, that's all I have to say. But I'm happy to take questions here.
No, that's terrific. Thank you very much, Laura. And very interesting time we live in, isn't it?
Yeah.
Now, I'm interested just in your opinion of something. Now, I photograph auroras and stuff. I live sort of on the northeast coast of Northern Ireland. Mm-hmm. I got some photographs on the 4th of November of the Aurora then. And actually, it was really quite an advanced, in terms of the cycle. It had rays and structure to it and so on. Whereas my recollection is that 11 years ago, all I was really getting at that stage was a green glow on the horizon. And now there are two variables that make a difference here. One is I've got a better camera now. And the other is I've got another solar cycle's worth of experience of finding out how to use it as well. But is this cycle actually starting off more quickly than the one before it, do you think?
Yeah, so I think that on the 4th of November, that storm that you saw, that was a particularly strong geomagnetic storm. And that was that X-class flare that occurred just on the very center of the sun. So we were directly in the correct way for it to come and interact with our magnetosphere to cause those aurora. It also had one of the largest solar energetic particle events associated with it. So it could be a combination of things, but I also think that that was a particularly large and geo-effective event to occur at the very start of the solar cycle. So yeah, hopefully more to come. I think the solar cycle is predicted to be quite similar to the last one. But yeah, that was just a very large and exciting flare, and a solar eruptive event to have occurred so early on.
Okay, that's good. Now let me just delve into the chat a bit, because we've got some questions here from. Now, first of all, Pat O'Neill, do you want to ask your question? You were asking about models to replicate the cycle and whatever. Do you want to ask your question, Pat?
Okay, Laura, thank you very much. That was a really interesting talk, and it is really exciting time in astronomy to see all these new satellites and all this new work going on. But we've known for probably hundreds of years now that the sun has this very regular cycle, 11 years for activity and 22 years roughly for magnetic reversal activity. Those are very regular cycles, but I just wanted to know, is there any modeling been done that could actually say, yeah, we can understand why it's 11 years or why it's 22 years?
Yeah, that's a really good point. It's like one of the aspects of solar physics where we have hundreds of years of data to go on. And it's actually one of the aspects I think that's really still quite debated. It's this idea of the solar dynamo. And I think there has been a lot of work recently. Now, to be honest, I'm not up to date on the how that is going. But there are really advanced models now that are really kind of getting down to the teeth of it to understand this 11-year, 22-year solar cycle. But yeah, and there's even kind of other cycles within that people are looking at. Is there kind of longer scale cycles that can also occur? But yeah, I think I don't think I'm answering this question right at all, but yes, there's lots of work being done and lots being figured out in recent years, particularly with lots of kind of dynamo models and using helioseismic observations to look at this. But I don't know if I actually answered your question there, Patrick, but apologies.
No, thank you, Laura. I appreciate this very complex system we're analyzing, but it's such a regular behavior,
Yeah. I guess to go back, yes, there are models that can replicate it for sure, and we have a good understanding of that. But I guess going down to the details of how large the next cycle will be, the magnitude of it, is something that's still quite debated. Or when does it actually flip from being solar cycle 24 to solar cycle 25, for example? Those intricate details are debated, but the large scale 11-year cycle is well understood and physically being able to determine and predict it. Yeah.
Okay. Thank you, Laura.
Paul is still muted. If I could come in just
I was going to say, Terry, you had a question as well, it said.
Right, okay. Just a very simple one. Why does the classification for flares go A, B, C, and then jump to M, and then jump to X?
Yeah, it's a very good question. And, they've only been labeled that way since kind of the late 80s with the kind of launch of GOES. And it really was because they had medium and extreme flares. And then they put it on a log scale and they was like, okay, well, we'll do A, B, C, M, and X. But it's just historical reasoning for people in the literature. I don't think there's any smart reason behind that. Because realistically, what you should do is, we have X, and then when it goes to a next order of magnitude, we don't have an XX, we have, or Z, we have a X10, X20. So maybe it would have made more sense just to follow the alphabet, but I think it just goes back to people looking at extreme and medium flares and then it going downwards. That's from my understanding.
Just another thing, as I say, Paul is still off there and I see he's on mute. We all know, or most of us know anyway, that this figure that the sun is losing mass at a rate of about 4 million tons a second through converting hydrogen into helium. Mm-hmm. But it's also emitting all the time a solar wind, and it's also every so often firing off CMEs. Are they a significant contribution to the overall mass loss of the sun, or is the hydrogen to helium conversion the main one?
It's a great question. So the amount of mass lost by the hydrogen to helium conversion is almost exactly the same as the loss by the solar wind, which is just a strange coincidence, I guess, of those energy conversions. But yes, but I guess it's still so small compared to the absolute size of the sun that it's not really going to have a significant effect for a very, very, very long time. We'll run out of fuel, I guess, before then. But yeah, I always thought that was interesting. The mass loss is similar in both ways.
Right, thanks. I see Paul's back there, so we'll hand over to him.
That's it. And I am no longer on battery power either. I'm on mains power. Right, Jerry, you had the next question up. Do you want to ask your question, Jerry?
Thanks, Paul. Laura, fantastic talk. Absolutely brilliant talk indeed. A lot of the questions I would have wanted to ask you, you did mention and you did cover about the other stars, for example, being quite unstable in comparison to our, with our observations, an awful lot more flares, an awful lot more energy given off. One thing I would like to ask is, I was reading about this Carrington event, and apparently they disconnected the wires from the batteries, and the electricity was still going through the wires. That's how powerful this is. It was really, really an amazing thing. And our society, modern society, is so dependent on electrics and electronics and satellites and communications. Is there any way we could minimize or even shield against a major Carrington event, something that's going to bring us back to before electricity, which would be a disaster for modern times? Is there any way we can actually, because it really brought home to be, even when they detached the batteries, in telegraph wires, they were still zinging, they were still going. So is there any ways we can do that with our modern electronics and modern electrics?
Yeah, that's a really good question, a really prominent one, particularly from any power grids that are interested in this type of thing. I mean, there's no way of stopping a solar storm happening. I mean, the idea is that we get better at predicting it. And if we knew, for example, a Carrington event was going to occur, it takes, maybe I should have mentioned this, when a solar flare happens, the radiation portion, that, when we see that, that's already happening. It's the speed of light. But the ejection, the CME, or the coronal mass ejection, that takes around 2 days to get here, maybe 3 days to get here. So if we knew that was happening, and we knew we had a good, which we do have good kind of models to understand how fast it is traveling and how quickly it will get to us on Earth, then we can do things like, in our power grids, the thing that would be affected is, as you said, like this current will flow through our power grids, and in the end, what causes the damage is that it overpowers the transformers. So one thing you could do is, if you knew this was coming, you could essentially open up all of your transformers to let the power flow. So that's one way you can mitigate it. Obviously, if it's so large, there's only certain things you can do. But the idea is that power grids don't have all their transformers open up at all times. So if you had something like that, that would be one way to kind of mitigate the damage. So yeah, it'd be things like powering down things, turning things off. For satellites, in particular, for satellite electronics, I know that people have been doing is like turning things off, or just letting power flow. But I guess we don't really know. We haven't had an event that has been so bad, right, in modern technology, in society. And just to kind of give you a good analogy is that in the UK Risk Registry, which was done a few years ago, they had a large solar event at the same risk registry as a pandemic, as a global pandemic, right? So now that a global pandemic has happened, people are like, well, humans are very bad at judging risk. But that's interesting, I find, that the risk assessment of a large solar storm, a Carrington-like event, is the same as a global pandemic. But again, I think there has been, I know like power grids like fund a lot of research, but again, it's usually closed source because they don't want to show the vulnerabilities of their own power grids. They do fund a lot of research into this, and I know they are one of the big kind of clients to, say, the Met Office for space weather forecasts and things like that. But yeah, it's interesting to think about what would actually happen if one of these happened.
Thank you, Laura. There's so much more we have to learn about our own star.
Yeah,
and it's complicated, with the magnetic fields and the considering this is mostly hydrogen and helium, and the vastness of this and the complexity of all these, the coils and complications of magnetic fields. It really is, we're learning, we have so much more to learn about it. We've found it an awful lot, but so much more to learn, and maybe start making predictions and, for our own society as well, to protect it from flares and things too. So thank you very much for that. It's brilliant. Thank you very much.
Yeah, just building on that point, I guess, I was very much on a space weather aspect today to be like, oh, the sun, this is why we should have studied it. But I think it's also really interesting from a plasma physics point of view, as Jared mentioned, you have these reconnection events in this large, we essentially have a large scale plasma ball in the sky, that conditions we can't create on Earth, but we can study to understand the physics going on. And one of the aspects is things like fusion reactors on Earth. So one of the problems they have is that in tokamak reactors, they have magnetic reconnection occurring and they don't fully understand it. So if we can understand it more in the sun, it's nice that using the sun as a lab, we can kind of feed into lots of different aspects of physics, which I think is super interesting.
Fantastic. Thank you very much. Brilliant. Thank you.
Great, Jay. Now, Andy, you've been imaging and you've got a question arising from that.
Yeah, thanks, Paul. Laura, just you might have already answered this question. Somebody came to the door there. That's the curse of Zoom, isn't it? I have a good answer. But there's this 11-year cycle and 22-year cycle. Where are the two? Is there two, or is there one, or where are we with that sort of cycle? Or maybe you've already spoken to that. I'm not sure. In
terms of the 11 versus 22 year.
Yeah.
Yeah, I guess it's because it's every 11 years. Say if the magnetic field line started straight up. Yeah. And then it's 11 years till they go this way, and then 22 until they go back to their original point of view. Right.
It really is a 22-year cycle.
Yeah, I guess if you go back to the original, but I guess in terms of activity, it's 11 years, right? So we see this maximum to minimum every 11 years, but from where it started to get back to where it started, it's 22.
Okay, it's as simple as that. That wasn't a question anyway. Apologies.
No.
I've got a new telescope, which a nice hydrogen alpha telescope, which allows me to take lovely, beautiful pictures. And one of the questions which is always in my head is the morphology of sunspots is so different. Is that something which studies and gives us some information about what's going on inside the sun? I mean, some of them are like bullet holes. Some of them are just like, plop, as if somebody had just fired something straight through the sun. And some of them are much more complex and diverse. And actually, some of them there in some of the images, I could see white splashes. And these things, I'm led to believe, are called element bombs, which I think are some interaction between the magnetic lines. Have you come across any of that stuff? Is there work being done on sunspot morphology and effects of that?
Yeah, absolutely. So with that, say, for example, with the Swedish Solar Telescope in the Canary Islands, and I know there's researchers at Queen's that are looking at this, active region flux emergence, what we'd call it, this magnetic field coming up from underneath to cause these sunspots. Why do we have some sunspots are just one single polarity but not that complicated? Then you have ones that grow that are massive beasts. So there's been lots of work trying to understand, why this goes back even to the activity of the sun. How does this flux emerge upwards from the tachocline, this kind of region where the magnetic field is generated? And we want to understand, I guess, how that magnetic field, why do some active regions emerge and then dissipate and don't flare? And why do some emerge and get more complicated and then do lots of flaring? So there's kind of lots of work going in, and we kind of understand, but we're still trying to get a better understanding of this flux emergence and how that leads then to cause this buildup of energy to cause a solar flare, for example. And I think these Elderman bombs are to do with this flux emergence, and strong magnetic field regions is where you see these. That's really cool. Could you see that in your H alpha filters?
Yeah, you can. Yeah. It's amazing, the detail. It's actually scary whenever you look at the detail. And it's also, just going back to your periodicity of the flares. I mean, at the moment it's quiet. The sun for the last 2 or 3 weeks has been reasonably quiet, whereas through October, towards the end of September, all through October, it was very active. And it's almost like your flare cycle. You're able to see the activity just with a simple. I mean, it's only a 60mm telescope, but it's producing beautiful information, and very simple at my level. But I'm sure a solar physicist could make a lot more information from it. Yeah.
No, that's really cool. Yeah, I do. Yeah, one of those things someday is I'd love to get my own telescope and have a solar filter on it. I'm just using data from instruments, and you lose the kind of disconnect, I guess, from actually looking at something through a telescope.
Yeah, no, super. Thank you very much. That's brilliant.
That's good. Well, Laura, thank you very much. That's the end of the questions we've got in the chat. Does anybody else have any questions they want to ask Laura about
Well,
her
you know
excellent
me.
talk?
I always have another one. Laura, first of all, an absolutely brilliant presentation, very, very clear, very comprehensive. So thank you very much for that before we go on. But you mentioned the European Solar Probe, but there's also the Parker Solar Probe, and there's also the DKIST telescope, which you say has just now come into operation on Hawaii. Do you have access or work with any of the instruments or experiments on either of those?
Yeah, no, you're dead right. I should have definitely mentioned those two. So the Parkway Solar Probe, yes, so we use some of the instruments. So most of the instruments in the Parkway Solar Probe are in situ measurements, and it's actually going to go really close to the sun. It's going to go, I think, within 6 million kilometers away, which is crazy. So one thing we're working on is it has a similar radio instrument to the instrument on Solar Orbiter, the radio instrument. And going back to this idea of having a stereoscopic view of the sun, it also helps when you have another instrument. So we now have Parker Solar Probe, we have Solar Orbiter, we have, satellites that are in Earth orbit. So when there are particular orbit patterns, we get this almost like complete 3D view of the sun. And I've been kind of involved in doing some work with triangulation of these. Can we pinpoint where the radio burst is coming from? And with DKIST, I mean, that's super exciting. I'm not particularly working with DKIST data, but I'll be collaborating with people that will be working on that. And we hope to use, say, for example, some coordinated observations with DKIST and the X-ray telescope on Solar Orbiter. So again, yeah, I should have highlighted those as well, but another really exciting time for solar physics. But yeah, all that data is well, with DKIST, it'll be a little while, but for example, with Parker Solar Probe and Solar Orbiter, all that data is open source and freely available to work with.
Great, thanks very much.
So, yeah.
Okay, that's excellent. Does anybody else have any questions they want to ask Laura before we say thank you very much? And no? Okay, well, Laura, you've been absolutely superb. That's a great talk. I think everybody's learned something from it. I certainly have. And so thank you very much for your time. Thank you very much to come and talk to us. And we hope to see you again sometime.
Yeah, absolutely. Thank you very much for the invite.
Thank you.
Thanks for listening there.
Terry, before we go, do you just want to tell us about the next one?
Yes, it's a talk slightly further away about the asteroids. And I haven't got an exact title yet, but it's Jamie Robinson, who was at Queen's, but has now just moved to Edinburgh. And he has promised me a synopsis and a biography